uh, a tutorial series on deep learning, and today we shall pick up on where we stop, which is how do we actually compute the gradient. We've already learned that for us to be able to adjust the numbers, the weight matrices, we need to compute the partial derivative of our laws with respect to the W's, the weights. And how do we compute the gradient? We can decide to do the gradient by using a paper and trying to walk through the gradient. And this will be very tedious because there are a lot of matrix calculus that we need to do. And if we change the laws, we need to rederive from scratch. And this will not be feasible for a complex model. So the best way is for us to use computational graphs with backpropagation. And that's the essence of this series. How do we build a computational graph? Now, this is a directed graph where each of the node in the input layer represent the feature or the variables, that is the independent variables. And we have a edge that goes from each of the nodes to other nodes in the layer. And we have a weight attached to each of these layers. As you can remember that the weights that are attached is actually the numbers that we're trying to adjust to give us the best possible numbers. So just some notations for us to know. You see here that we calculate Z1, Z2, and Z3, and after we are done with that, we take it through an activation function which will give us A1, A2, and A3. Like I mentioned in previous tutorial, I always see A1 as like a transformed X1. I see A2 like transformed X2. That's what we actually call it activation function, activation map, or you call it feature representation. Okay. So we represent our neural net equation as a graph, like we can have in this list. This is we have 3 inputs plus the bias. So these are input. The interior knows whatever operation that we want to do. The operations actually takes place in the nodes. What essentially each node does is it either holds a data or holds a computational a computation. So edge pass along the result of the operation, and in our edges are the numbers, which are the weights. So for Z1, in order for us to calculate Z1, we need to first of all take in all the edges that comes to Z1. In this case, we have 1, 2, 3, 4. So we're going to have those edges that are coming. That means you have four weights coming into that. Then we have our x1 up to with the bias. So we have our x1, x2, x3 plus the bias. So what do we do there? We multiply the weights by x plus the bias. Those are bias. So here we have 1, 2, 3 coming into Z1. So we multiply the W, which our random gets W1 multiplied by X1 plus W2 multiplied by X2 plus W3 multiplied by X3. Then we get this. Then we have the bias. After we are done, then we pass the Z1 through the activation function. Let's say we have chosen sigmoid. So we pass this into the activation function, sigmoid, to give us the activation map. Okay, we do the same thing for Z2, which will be the W, the weight matrices. This one, this is 1, 2, 3 that comes into this node. We multiply it by the axis. We had the bias. Okay, So the bias will be the same for all of them. Then we pass this into the sigmoid function and we get our next activation values. So we continue like that until we are done up to A3. So excuse me. So now this is just what I've explained in the earlier part. We take our x, we take our w, multiply our w with x. Remember, this is a vector and x is also a vector. We add the bias to it, we get our z1. We pass our z1 through the activation, we get our a1. Then that is that for the first one. The second one too, we do the a2. For this one, we do the w2 and the a1 as to be able to get this one as we continue. So the result that we have the w2 and the a1. We multiply, that is to the next layer. We're going to the next layer here, that is into this place. So we continue like that until we actually reach the final prediction. So this is our final prediction, A2, that's our y hat, and this is our original target, given target label. Then we determine what is the loss between the predicted and the actual. Okay, so this is a simplified representation of what a sigmoid actually does. The sigmoid function can also be represented as a computational graph. Now, in the next lecture, we shall look at back propagation. How do we back propagate to be able to update these numbers? Thank you for listening. Do let us know what your comments are.